Okay, so to continue what we were doing, I have copy pasted all the content of previous node, node 27, in this node, this new node, and then run all of them together as one whole cell in one whole cell. Okay, so what I'm going to do now, I'm going to get the component loadings of this data set. So the correlation coefficient between original variables and the component, that will be the component loading, and that's a kind of the squared, actually the squared loadings within the PCAs sum to 1 always. So we will see what loading exactly is. So I'm going to talk about component loadings, which is the correlation coefficient between original variables and the components. And squared loadings within the pieces always sum to 1. Okay, so how we get loading? We write down loadings equal PCA dot components, and let's see loadings for now. We have a matrix. I want to see if I can get the shape of this. So look at this. We had 2,544 variables, and the matrix we are getting is a square matrix, 2,544 to 2,544. Means this will be the correlation between the components and all the variables, or in parentheses we call the variable samples in this data set. So last time we saw that what is the number of PC. We said we can use PCA.n feature, and then we can go get all the number of PCA. So as we know, the whole number of PCA is 2,544, right? And then we already created label. Let me bring that here, this one, and now I'm going to create another variable loadings, create a data frame. I'm just creating a nice data frame for the matrix, that matrix of loading. So I'm using dictionary and zip, and then I'm going to use the labels and the loadings, this one. I'm going to give them a label using this method here in the data frame, and I'm going to create variables column, and I'm going to say these are all gene exp scaled dot columns dot values, and I am going to actually here loadings and sorry, this one, and then I'm going to say loadings is, let's say set the index underline index, and this is going to be the index for loading. Okay, so this, let me check this. So let's run this to see what happens. Oh, okay, object. Oh, okay, this one should be the original matrix. We are getting column values for from the original matrix. Okay, good. And then we are going to show the loadings like this. Okay, so what we have here, we have a nice correlation coefficient matrix of all the components, principal components, and the variables. So next we can create a, let me actually, let's show you what exactly we want. We want only the first, let's say 8 components, right? So these are the only components we want, and then we want them to show all the samples in this way. Okay, good. So these correlation coefficient between original variables and components, these numbers are negative and positive, right? These negative and positive values in component loading, these are reflecting the positive and negative correlation of the variables with the PCs. And so what, let's go back to the first lecture that we start principal component. So what was the whole aim of principal component? We wanted to reduce the data set to a data set that can explain the variables very well. So we had samples in our columns of data set, and we had gene in the row, right? And then what we wanted to do, we wanted to choose the samples that are explaining the data set, explaining the genes very well. So what we did, we created principal components for samples, right? Now we want to choose the best principal components that explain these samples. Let's say we choose just 3 principal components, means out of all these samples, we don't need to, use samples anymore. These principal components are going to explain the genes very well. If we even choose 3 of them or 4 of them, we don't need all the 2,544 samples anymore if we choose just 3 of these principal components to explain our data set. So we should only keep those principal components that explain the most variance. Again, 75% to 95%, for example, to make the kind of interpretations much easier for us. And this more the PCs you include explains most variation, right, in the original data. But sometimes experience says if you choose like instead of just choosing 4 best principal component, if you choose 10 of them, you sometimes will kind of ruin the data set you are creating. If 4 is going to explain 90% of the variation, that's good, that's enough. You don't have to exceed more than that, but still this is kind of subjective. And again, the eigenvalues for PCs can help to retain the number of PCs, and generally these PCs with eigenvalue greater than 0 contributes greater variance, and they should be retained for further analysis. So we also draw a script plot that shows which PCs are important. And now the other plot that I'm going to show you using Seaborn as SNS import. Actually, we already import matplotlib. And then I'm going to write down AX equal SNS dot heat map. Heat map is a really amazing plot that can help you to show a high dimensional data set in a really easy and more kind of understandable way. So let's say I'm going to choose all the, let's say 1 to 0, 1 to or 0 to 0 to 50 samples, for example, and I want to choose just the first 5 principal components, and let's say 8, because over and over I'm saying 8. I don't want to create confusion. And what else? I'm going to say annotation true, and then C map. We already saw C map, and this one we want to use a spectral, and then let's see what happens if this is okay. So what we have here is very messy. Why? Because I chose 50 sample. I just I mean, if I want to choose more sample I can, but I should adjust in kind of squares everything in a better way, and I don't want to waste time. But you can always choose more and then change the dimension of graph, change the notation, everything. Okay, so what we see here, this is a heat map plot that shows all the samples on the y-axis and all the PCs on the x-axis, PCs that we were choosing. I chose 8 of them, right? Let me show another one that I'm just choosing 3 PCs. Just 3 of them, and then this shows the correlation between PCs and the samples, right? How the PCs are explaining each sample. And then we have negative sign here, means negative correlation, positive correlation, right? So the blue, darker blue shows the higher correlation between, for example, PC5 and this sample that we have here, right? And then we can actually show all the samples to see which area is more kind of higher correlation. For example, these PCs, 3 PCs, do you see that? These are in compared to the rest, not here. Here when I zoom in, it's comparing 3 PCs, but when we are zooming out and we have more PCs, these are going to be compared with more PCs, right? And then it shows the first 3 PCs actually have a good correlation, positive correlation in compared to the rest with the samples. Means these are explaining the sample much better than the other PCs like PC 8 or 7. Let's reduce this to 6 and see how PC 1, 2, 3, 4, 5, 6 in comparison to each other. Yes, see, when we are kind of zooming out, I'm saying zooming out means I'm choosing the less number of PC and the graph is kind of zoomed in, right? This one is zoomed out. So we see that PC6 has a negative correlation with one of the sample, another sample, another sample. So in compared to PC 1, 2, 3, these PCs are not doing good. So now you see what happens. We can finally in conclusion get just 3 PCs in our data set and use these principal components and explain the genes very well. This is all we do in high dimensional data set. We reduce the data set to the component that can explain the data set much better, and then we use this data set to kind of draw a graph, explain the gene, or further analysis also. Okay, so now what we want to do, we want to use this loading index and draw another plot. Okay, we call this plot PCA plot. Okay, so I'm going to again define the explained variance np dot round PCA dot explained variance ratio multiply 100 decimals equal to. Then I'm going to adjust the figure size to 12 and 8. And I'm going to plot a scatter, and I'm going to use loadings dot pc1 and loadings dot pc2, and then I'm going to make this graph fancy. I'm going to say X labels that I know are going to be PC1 information. I'm going to create percentage, format this to explained variance, the index 0, because we know we are getting the explained variance ratio percent of this for PC1, and then for Y label I'm doing the same thing, PC2. So I am drawing a scatter plot of PC1 versus PC2. And then what's the title of graph? Title is the PCA graph, PC1 versus PC2. It says loadings. Okay, what else? It's not defined. It is loadings, yeah. Loadings. What else? Oh, what is that? X labels. Again? What's wrong with me? What happened now? X label. X. I feel I did it correctly. Is that EL? I think so. Yes, okay, good. Okay, so what I did, I draw a scatter plot of all the genes, PC1 versus PC2, and it shows PC1 is 70%, PC2 is, oh no, PC2 is not 70%. PC2 is the index one, right? So now let's see what happened. Okay, good. We see all the genes tend to go in a positive direction of PC1, component 1. The weight on this side is heavier, and they are around the 0 if you draw a line here, and mostly on the right side of PC1 tend to go to the positive side of PC1. Okay, so what I want to do, well, now our sample names are very messy. Imagine if we had a better sample name, a smaller, we could create a for loop. Let me create a for loop. I say for sample in loadings index. What was loading index? Let me see, show you. So these are the sample name, right, in loading index. So for a variable that's the empty variable like I or J, for a variable sample go through the loadings index, which is the samples name. Okay, so we are creating for loop. What I want to do, I want to say use annotate, and then what annotate is doing, it's going to assign a name, write down a name for each point. So the name is coming from loading index, right? So sample starts from the first name, gets this name, put this here. And then what else we do? It will create a tuple which has a x and y value. X is PC1, Y is PC2. So now what we do? It's kind of difficult here. Loadings PC1 LOC sample. Okay, so let's say okay, let me write all of this down, and then after run the loop, I will show you exactly what are these values coming from. So what it does, it will get the name, put the name here, and it will go to the location in this matrix, in the loading PC matrix, and find the name of sample, and then find the PC1, which is a value, numerical value for that sample, and we'll write it down here. And then it will choose the PC2 for that specific sample, the name of sample, right? So it will have an X value, Y value for the point. So this tuple here is the point XY, and then this information here is the sample name. So let me see if everything is okay. So if I run this dot, if I run this, it's going to take a time to load this. Still loading. So okay, here it is. It's so kind of messy. I don't like it, but imagine if we had a bigger graph and each of the name were shorter. We would have a point, would have a kind of name for each of this point, right? And then we could see what samples are together. For example, day 10, these 2 points are coming from sample of embryo at day 10, right? So you would see it more clear as a cluster. Okay, so what I want to do, I want to do something else. I want to copy all of this, paste it here. Do you remember what those gene information, the path 2 was? The path 2 was the gene information, right? Let's bring it here. Path 2, which contained the gene information. This one, right? Okay, so what I want to do, I want to separate these points to cell type or gender, right, of embryo. So what I'm going to do, I'm going to create a loop, which is kind of more difficult now. What this does, it says for. Let's say instead of sample, I say cell. For cell in lineage. So it's going to go get the sample, for example, starting from here, get this name right in the lineage. Actually, I'm going to define the lineage. Let me define that. I forgot to define that. So if this one is gene information dot lineage dot to numpy, and this is going to be named lineage, and then I'm going to print lineage for you so you know. But okay, good. So I got the column lineage and then changed it to numpy, right? Convert column lineage to array, and here it is. We have this, right? And then there are EPI cell also type here. Okay, so it will get each element in order, each element of lineage, and then what it does, it's going to annotate plot, put this cell name type here, right? And then what it's going to do, it's going to, oh, I didn't show you what is loading sample look like. Let me show this to you. So this is just a value, a number. For example, sample, let me see what was the sample. So it's normally going to get the last sample that went through a loop. So for this sample, for example, the loading will be PC1. Okay, so now what I'm going to do, I'm going to say get the cell type, use annotation function, paste the cell type name using the PC1, PC2, the way I was getting the tuple for each sample, right? Same way, instead of sample, I'm writing down J. And then here I'm going to define a start J from 0. So if I start J from 0, what happens? It will go to location 0, PC1 for the 0 sample, for the sample 0, right? And then the cell type also goes here, starting from here, the row 0. And then when the first loop finishes, I should increment the J by 1. So then it will go through the next sample. Then when loop finishes, it will increment J by 1. Increment J by 1. Here, start with sample 0, right? Okay, so let's see what happens if I do this. I hope everything is fine. No, it's not. Did I explain the lineage? Defined it. Let's define this one again. And then this one says return self yet as error. Oh my God, I'm sorry. I'm going to loading index. Yeah. So loading index had the sample name, right? I will get loading index J. How did I forget? Means sample J, because loading index was the sample, right? So here I'm going to write down loading index is the sample jet. Okay, so now it's going to work. Okay, so as you see here, this plot shows each cell type. So PE is a cell type, PE is a cell type. So when our data set is a kind of more, if the clustering is organized and we have a really clear cluster, what happens, for example, all of a sudden you will see all the points on this part are cell type PE, right? All the points in here are cell type TE. But here it shows that there is no clear or obvious cluster between cell types. First of all, if we go to gene information, we will see there are not that much of sample EPI, cell type EPI. So the distribution is not kind of the kind of chance of observing each of these cell types are not equally likely, because this data set has mostly cell type TE. And if I even want to show the gender, most of genders of embryo is the gender female, right? Okay, so we can change the column and then we can show different attributes. And also if you're more curious, you can study this more and see how you can change the color of each point based on the sample type, and that would also create a nice clusters for you. Okay, so this was about PCA. I hope it was helpful, it was beneficial for you. Let me know if you have any question. I hope you have a good day. Take care of yourself. Bye.